In the previous exercises, we've been talking about the formation of acetals from either aldehydes or ketones. So you could have some sort of a ketone, and you'd treat it with at least 2 equivalents of alcohol. Usually they'll just write excess. So here I'll write the other equivalent in. And then you end up getting an acetal. So we've spent some time talking about that so far. Now notice, when you get this, you do have that carbon chain still, so that stays the same. You also have the OR groups, that all stays the same. But notice what is left. Outside of that, you have 2 hydrogens and you have an oxygen. Those come together to give you water. Another thing to notice in the acetal reactions that we've been talking about is that every single step was an equilibrium step. Every step went both forwards and backwards. And what that means is that you can not only take a ketone and form an acetal, but you can take an acetal and form a ketone. The two exist in equilibrium at any time. Now the way you can control that is with Le Chatelier's principle. Remember, you can think of an equilibrium as sort of a water tank, with the left side of the water tank representing the reactants and the right side representing the products. And if you remove water from the tank or you pour water into the tank, it's like removing or adding reactants or products. Now if you have an acetal and you want it to come apart in order to go backwards to form the ketone, all you'd have to do is add water. Adding water is like adding a product. Imagine pouring water to the right side of this water tank. The water would ultimately flow to the left side. Equilibrium would shift to minimize that change. You wouldn't just have a big chunk of water there. The equilibrium would shift. It would move to the left to minimize the amount of water that goes up there. It would minimize that change. So, if we add water, then we will break apart our acetal and will form our aldehyde or ketone. Okay, now we've said that in English. If you wanted to say that same thing in Greek, you can take an acetal and you can do hydrolysis. So if you add water, hydro for water, like you hydrate when you drink water, and you use it to break apart lysis, break apart your acetal in order to get the ketone, then you're doing hydrolysis. You're adding water to break that molecule apart. In general, the suffix lysis means to break apart. For example, if you analyze something, you break it down. And if something is an electrolyte, it breaks apart because of the electrical charge that it has. Or hemolysis is the breaking apart of blood cells. So in general, that lysis means to break apart. So we're going to do hydrolysis on some acetals, and what that really is saying, that's just fancy speak for doing the reverse of the reaction we were just doing. Instead of taking a ketone and getting the acetal, we're going to take an acetal and get the ketone. So that's what they're talking about in exercise 2012, drawing the mechanism for the hydrolysis of acetals. And you'll notice we have an acetal and H3O+, just some type of acid catalyst to make that happen. That's all we need. And we'll get a ketone out of this. Now we want to be able to draw the mechanism. So let's think about the mechanism that we've already sort of built up. We've already built up this concept in our minds that if you have a ketone, you can use it to get a hemiacetal, and then the hemiacetal you can use to get the acetal, using these steps that we've seen so many times. If we want to go in reverse, we would really do the same steps, but in the opposite direction. Now, a proton transfer, that term signifies both putting a hydrogen on, putting an H+ on, or taking an H+ off of a molecule. So if we put it on a molecule before, now we're going to take it off. But that that opposite process is still referred to as a proton transfer. So we don't have to change the terminology of these proton transfers for the reverse reaction. We'll just be transferring a proton in the opposite direction. But what we do have to do is change the terminology of nucleophilic attack and loss of a leaving group. Let's say you had a molecule, say you have a carbocation, and some sort of nucleophile with a full negative charge comes in and attacks it. Well, then it sticks onto the molecule. But play that same process in reverse. I'm going to rewind, and the nucleophile comes off of the molecule. In other words, it's not acting out like a nucleophile, it's acting like a leaving group. So what in the forward direction is nucleophilic attack, in the reverse direction is loss of a leaving group. So we'll switch these nucleophilic attacks with losses of leaving groups. So instead of nucleophilic attack here, in reverse, as we go in the reverse direction, it won't be nucleophilic attack, it will be loss of a leaving group. And here again, instead of nucleophilic attack in the reverse direction, it will be loss of a leaving group. Okay, then if we go in reverse, let's think about this loss of a leaving group that we had originally. Let's think about what happens with a leaving group. You have a molecule with a leaving group on it. And with loss of a leaving group, the leaving group takes its electrons and goes away. So that's in the forward direction. Let's rewind that videotape. The leaving group comes back, sticks on the molecule. In that case, it's really nucleophilic attack. It's something with electrons going to a place where there are missing electrons. So if the forward reaction is loss of a leaving group, the reverse of that same process is nucleophilic attack. So where we had this loss of a leaving group in the original molecule, now we're going to have nucleophilic attack. So in the reverse direction, we're going to have a very similar journey, a very similar set of steps, flowchart. We're going to go from the acetal to the hemiacetal, and that process is going to be bookended by proton transfers. But what was nucleophilic attack is now loss of a leaving group, and what was loss of a leaving group is now nucleophilic attack. And likewise, as we go from the hemiacetal to the ketone, the process will still be bookended by proton transfers, but what was nucleophilic attack is just going to be loss of a leaving group. And so this is our process. These are our steps. So let's organize those for this first one. Let's just place those first together, and then we'll organize these separately. Okay. Well, the acetal that we're starting with is what they give us. And ultimately, we're going to want to get to a ketone. Or it could also be an aldehyde. In this case, it will be a ketone. In between, the halfway mark is the hemiacetal. So let's draw those structures in so that we can sort of have landmarks to keep our eyes on as the reaction goes by. Well, the acetal is exactly what they give us. So no trouble drawing that, we're just copying it down from here. In the hemiacetal, one of those ethers is going to come off and turn into an alcohol. So for the hemiacetal, we'll still have this carbon ring, these carbons. One of those ethers will still be there, but one of them will be an alcohol. And the bond that was going to the other one will be going to an OH. That's our hemiacetal. It's bonded to an ether on one side. A carbon is bonded to both an ether and an alcohol. That's our hemiacetal. Finally, the ketone we'd have is the same structure as the acetal, but where we had the two ethers bonded, that's going to be just the carbonyl. Now, if you wanted to follow these, you have your alcohols. To get the hemiacetal, you have to add this new OH. And it's ultimately that oxygen that turns into the oxygen on the ketone. Okay, so these are our benchmarks. Now let's take these steps and we're going to put them in order so that as we go through, we don't get lost. Nucleophilic attack after nucleophilic attack. For this first part, we'll do the proton transfer. At that point, we should have our landmark, the hemiacetal. And then begins the journey from the hemiacetal to the acetal, a process bookended by proton transfers. Sandwiched in between them is a loss of a leaving group. Okay, so there's our process. General outline. So let's take our acetal. We're starting here. We're going in this direction. So we'll take our acetal, and the first thing we want to do is a proton transfer, and this is going to be to make one of the oxygens in the ethers a better leaving group. Ultimately, we want both of those oxygens to come off, so we want both of these to act as good leaving groups, but right now they're terrible leaving groups. If one of these oxygens took electrons and popped off, you'd have an oxygen with a full negative charge. And that's, since oxygen is such a small atom, that's a very unstable arrangement. So we have to turn, and because it's unstable, it's a bad leaving group. Because if it tries to leave, it will be unstable. So we need to do a proton transfer at first, and we can do that using the acid catalyst that they give us. So that is this hydronium here. So the slightly negative oxygen in the acetal will attack one of the slightly positive hydrogens in the acid. The electrons that were keeping that hydrogen on the molecule will snap back onto the most electronegative place nearby, and that's that oxygen. So there's our proton transfer. It will give us basically the same molecule, it's just that that oxygen will have instead of having a lone pair, it'll have a hydrogen bonded to it. And that gives it a full positive charge because it has 3 bonds. Well, now it's an awesome leaving group. All it needs is a slight push, and the leaving group will come off. And the push comes from the oxygen next door. The carbon in between is pretty slightly positive. It's, after all, bonded to 2 oxygens that are stealing its electron density, and so the electrons there have been eyeballing it this whole time. Well, now, when they try to swoop in and form a new bond, we have a good leaving group that can get kicked off. So we have loss of a leaving group. And what we form after that step is something very close to the hemiacetal. We have a double bond to the oxygen on the left. It still has 1 lone pair. That will, on the other end, this oxygen will no longer be bonded to the carbon chain there. It leaves as an OH. The oxygen here has 3 bonds, so it has a full positive charge. Okay, well, we've seen this before in the acetal mechanisms. We have this oxonium ion, a carbonyl with the oxygen having a full positive charge. That steals electrons really well from that carbonyl carbon. This carbonyl carbon is an amazing electrophile. It doesn't take a lot to get that to attack. The nucleophile it's going to attack, because remember what we're ultimately trying to do is get an OH on there. The nucleophile it's going to attack is going to be water. Now, if you were tempted to add OH minus, remember that you can't. You can't in this reaction because you're using an acid catalyst. If you try adding OH minus to the solution, it'll just be neutralized by the acid catalyst. And instead of making the reaction happen faster, or you'll just be taking the acid catalyst out of the solution, and so it may not even happen at all. So the nucleophile you can use is water. It's a weak nucleophile, but then again, we have such an amazing electrophile, it should still be able to react. So the slightly negative oxygen on that water is going to swoop in and attack the carbonyl carbon. The pi electrons, it's easy to break a pi bond because there's that interrupted overlap. The pi electrons get kicked off and they go to the most electronegative place nearby. That's the oxygen. they go to help to stabilize that full positive charge. Well, what we're left with at this point is something very close to the hemiacetal. Not quite, but very close. We have the alcohol, or the ether, I should say. We have this ether on one side. On the other side, we have the water that added. Now that oxygen has 3 bonds, so it has a positive charge. So, this is our molecule now. It's almost the hemiacetal. It's just unstable because of the positive charge. We can get rid of that by taking a hydrogen off there. And so another water molecule can come in and act as a base. This water molecule swoops in the slightly negative oxygen, steals the slightly positive hydrogen. The electrons snap onto that oxygen there. And we are left with our hemiacetal. And actually, let me draw that bond. So our hemiacetal here. We have an ether and an alcohol bonded to the same carbon. That's our hemiacetal. Well, we are almost done. We just have to make the journey from the hemiacetal to the acetal. And to do that, we want to kick off this ether. We want that to act as a leaving group, but right now it's a terrible leaving group. If this were to take its electrons and try to leave, you'd have a full negative charge on an oxygen atom. That's very unstable. So we have to turn that into a better leaving group, and we do that by doing a proton transfer. We can take one of the H3O pluses that we've made in the previous steps, and the slightly negative oxygen can attack the slightly positive hydrogens on that hydronium. The electrons that were keeping the hydrogen there snap back onto the oxygen to help stabilize the positive charge on that oxygen. Now that is a proton transfer. So that's what we're doing here. And what we'll be left with basically the same molecule. We'll be left with basically the same molecule, but this lone pair will just be bonded to a hydrogen. That gives the oxygen a full positive charge and makes it an amazing leaving group. Now all it needs is the slightest push. And we also formed water here. The slightest push, and this will leave the molecule. Well, the push comes from the oxygen nearby. That oxygen is slightly negative, and the carbon right next door to it is slightly positive. It's losing electron density to the 2 oxygens, and so the lone pairs there have been eyeballing that positive charge this whole time. Well, now they swoop in and attack, and because the other branch is such a good leaving group, that gets kicked off. Takes its electrons and leaves. And so that is our loss of a leaving group. Oops. So if we're keeping track of these steps, we have this proton transfer up here, this other proton transfer. Now we're at loss of a leaving group. So we end up getting this molecule. Oxygen has a full positive charge because it has 3 bonds, and outside of it we have this here, which is called ethylene glycol. They use it as antifreeze in cars. Well, we're almost at our ketone. We just have to get rid of the positive charge and the hydrogen. And we can do that by doing a proton transfer. We can add one of the waters that we've made, and the slightly negative oxygen there can steal the slightly positive hydrogen, have the electron snap back onto that oxygen, help it to stabilize that positive charge, so that there is a proton transfer. And that would give you your ketone and your acid catalyst. So that would be the end of this equilibrium reaction. So this is really the same reaction we've done before, but in reverse. You need to get the two ethers off of your carbon chain, so you turn one into a good leaving group with a proton transfer. Then you have the loss of that leaving group. You do a nucleophilic attack to bring in the oxygen that will ultimately become the ketone oxygen, carbonyl oxygen. You have to stabilize that once it gets there. You do that with a proton transfer. Then you have the hemiacetal. You want to kick the other ethoxide off, the other ether off. So first you have to turn it into a good leaving group. You do that with a proton transfer. Once it's a good leaving group, it gets kicked off, so loss of a leaving group. And then you basically have your ketone. You just have to stabilize it with a proton transfer, and you finally get your product. So we'll be doing a few more examples of these. I'm going to do this in a separate video so that the videos don't become unduly long. But you can see that if you know the flowchart for the original process, all you have to do is switch loss of a leaving group and nucleophilic attack with each other and go in reverse. And you'll start to see patterns in that the proton transfers are just stabilizing charge, and the nucleophilic attacks are bringing in this case, the ketone oxygen, the carbonyl oxygen, and the loss of the leaving groups are kicking off the alcohols, or the ethers that are already in the